8.3, three-dimensional vectors. So, vectors in three-dimensional space can be described by coordinates in a way similar to the way we describe vectors in a plane. So, normally we have an x-axis and a y-axis. Here, the x-axis is, when we're talking about vectors in 3 dimensions, the x-axis comes out of the page or out of the screen towards you. And the y-axis goes left to right, and the z-axis goes up and down. So a vector in 3-dimensional space is going to have an x, a y, and a z component. So you can have a point here that would be like the corner of this cube. All right, if you imagine a cube like this, you can have a point there that would be the corner of the cube. Each point in space corresponds to an ordered triple of real numbers. To locate a point P with coordinates x1, y1, and z1, you go x1 units on the x-axis, you go y1 units on the y-axis, and then you go z1 units on the z-axis. And that's your point. I'm not going to make you draw things in 3 dimensions because that's just not any fun, and it always looks like a disaster. So, locate the point at -4, 3, 2. It's literally going to be -4 units on the x-axis, so backwards, and then 3 units on the y-axis, and 2 units on the z-axis. There's your point. Ordered triples are like ordered pairs, except there are 3 numbers instead of 2 of them. They can be used to represent vectors. The geometric interpretation is the same for a vector in space as for a vector in a plane. It's still a directed line segment from the origin to whatever the point is. And you write a vector, x, y, z, where x, y, and z are the coordinates of the point. To find the length of a 3-dimensional vector, we just expand the Pythagorean theorem to encompass 3 dimensions. So instead of a squared plus b squared equals c squared, it becomes a squared plus b squared plus c squared equals d squared, where d is the length of the vector. And if you solve for d, you take the square root of both sides, you get d equals the square root of a squared plus b squared plus c squared. It is very, very easy. You just add a third term in there. So write the ordered triple that represents the vector from x, 5, -3, 2 to y, 4, -5, 6. So just like with the 2-dimensional vectors, it's harder to draw this, right? With the 2-dimensional vectors, we could draw them and use the graph as a reference. It's harder to draw them with 3-dimensional vectors, but we can find the difference by subtracting the 2, right? So before we subtracted the 2 points in order to find the vector between them. So the x is going to be 4 minus 5. The y is going to be -5 minus -3. And the z is going to be 6 minus 2, which is going to give us the vector. Technically, these should be brackets. It's going to give us the vector, -1, plus 3 would be -2, 4. All right, subtract the x-coordinates, subtract the y-coordinates, subtract the z-coordinates. And that'll give us the vector from point x to point y. Entomology is the study of insects. Entomologists often use time-lapse photography to study the flying behavior of bees. They have discovered that worker honeybees let other workers know about new sources of food by rapidly vibrating their wings and performing a dance. Researchers have been able to create 3-dimensional models using vectors to represent the flying behavior of bees. Suppose the flight of a honeybee passes through points at 0, 3, 3 and 5, 0, 4 in which each unit represents a meter. What is the magnitude of the displacement the bee experiences in traveling between these 2 points? So first of all, we need to find the vector that goes through these points. So we're going to do the second vector minus the first vector. So 5 minus 0, 0 minus 3, 4 minus 3. And that gives us the vector 5, negative 3, 1. We'll call this vector B because I think I'm funny. Then the magnitude of vector B, we just do Pythagorean theorem, square root of 5 squared plus negative 3 squared plus 1 squared, which is the square root of 25 plus 9 plus 1, square root of 35, which is just a little bit less than 6. 5.9 meters. Find the ordered triple that represents 3p minus 2q if p is 3, 0, 4, and q is 2, 1, negative 1. So 3p, right? Just like with our two-dimensional vectors, we multiply all of the coordinates by 3. And so that's going to be 3, 0, 12. And 2q is going to be 4, 2, negative 2. So 3p minus 2q is going to be 3 minus 4 is negative 1, 0 minus 2 is negative 2, 12 minus negative 2 is a positive 14. Three unit vectors are used as components of z-vectors in space. So the two-dimensional vectors we can write as the unit vectors I and j, where I is 1 unit in the x direction and j is 1 unit in the y direction. Now we also have a unit vector k, which is 1 unit in the z direction. And just like with the two-dimensional vectors, we can write any vector as the sum of unit vectors. So like if I have some vector that is 2, negative 3, 5, right? I can write that as 2i minus 3j plus 5k. 2 units in the x direction, negative 3 in the y direction, 5 in the z direction. And that's it for 8.3.